In the previous session, we discussed about the stress, strain, and Hooke's law. We know that Hooke's law is a linear relationship between stress and strain, and the material was axially loaded. But the question is, what happens to the strain in the direction perpendicular to the load direction? We all know that when we elongate a material, as the length increases in one direction, the cross section will reduce in the other perpendicular directions. This can be practically seen when we use a rubber, and if you stretch it, we know that the length is going to increase enormously, thereby reducing the cross section in the perpendicular directions. In this session, we are going to define such kind of behavior, and we are going to take it into account, and we will find how we can relate it mathematically. To know to relate mathematically, we have to understand what is Poisson's ratio. Poisson's ratio are being denoted using these three these variables. So these are the conventionally used way of notating the Poisson ratio. So the material is considered as homogeneous and isotropic. Homogeneous is a very common type of assumption that we use across materials, mechanics of solids, wherein which the material is considered uniformly distributed throughout. And isotropic means the material is having same property in all the perpendicular directions. If you move along the x or y or even z, the property remains same. And Poisson's ratio is defined as the ratio of lateral strain to longitudinal strain. In simple words, we can say that Poisson's ratio is the ratio of strain in the perpendicular to load direction divided by the strain in the direction of the load. Suppose if we apply a load in the x direction, if you look at this figure, you can see that the load is applied in the x direction, and that particular direction is considered as the longitudinal direction, and anything perpendicular this loaded direction is called as the lateral direction. So in this case, the y direction as well as the z direction are the lateral directions. And if we consider this uniaxial loaded member, we know that the length is increasing in the x direction and decreasing in the y and z direction. We can see that the length L has decreased delta L in the y as well as z direction, but elongated in the x direction. So if we look into the equation of Poisson's ratio, we can say that it is nothing but epsilon y divided by epsilon x, and epsilon y is nothing but mu into epsilon x. Epsilon x is nothing but stress by E. So we will get the equation of strain perpendicular to the x direction as mu into sigma x by E, and the negative sign implies that the stress, or the not the stress, strain is decreasing, or the strain, the length got reduced, and the direction is being accounted using the negative sign. This is a uniaxially loaded member. Now we are going to see what is going to happen in the biaxial state as well as the triaxial state. And the normal range of Poisson's ratio is 0 to 0.5, and generally for engineering materials that is varying between 0.25 to 0.333. So it's a very close range. So if you look at the different engineering materials, that is going to be within this range. But there are materials which is having some extreme behavior. Suppose if you go for the rubber, the Poisson ratio is almost equal to 0.5, and there are materials which is having Poisson's ratio 0. So we will discuss about all those details in the coming slides. Now we have to look into the biaxial as well as triaxial state. So if we consider in the 2 dimension, the material is loaded in the x as well as y direction. We will consider this as the x direction and this as the y direction. So consider this as the x and this as the y direction. So the load is only in the x and y direction. First let us take the x direction alone. So what is the strain along x direction? It is simply sigma x by E. By the Hooke's law. But if you consider the load in the y direction, then the material will not undergo that much amount of deformation when we consider the x direction only. Because when the material tried to deform more in the x direction due to the load in the x direction, the load in the y direction will pull it on the other side, and thereby the net effect will not be as much as when we compare the first one. So it was supposed to elongate sigma x by E, but because of the load in the y direction, the length, some reduction in the length has happened, and that is mu into sigma y by E. It's a very simple concept. Take some time, try to imagine and try to learn. So when you apply load in the x direction, it was supposed to elongate sigma x by E. But when we apply a load in the y direction also, along with the x direction, it will not permit the strain to go up to sigma x by E, and it will reduce that strain to a limit mu into sigma y by E, and the net strain in the x direction is going to be sigma x by E minus mu into sigma y by E. And this minus indicates that the reduction happening. And if you consider the y direction also, same thing, sigma y by E minus mu into sigma x by E. Because if you consider the y direction, the strain was supposed to be sigma y by E, but due to the pull in the sigma x direction, the total elongation was limited to sigma y by E minus mu into sigma x by E. There is no need to consider this equation right now, because you may feel confused. Let us forget about that. That can also be considered. If you consider some y z direction or zx direction, this is going to be the equation that we will write. So this is the case of the biaxial state. Now there is a question regarding the sign. See here, sigma x by E was in tension and it was supposed to elongate, and this elongation was restricted, some amount got decreased, that's why a negative sign. What if the load in the y direction was compressive? The answer is very simple. If the load in the y direction was compressive, that means if you have a load in the y direction is compressive, what will happen? This load in the y direction will assist the load in the x direction to increase the length. Try to imagine what will happen when you apply a tensile load in the x direction and a compressive load in the y direction. Obviously, the length in the x direction is going to be more due to the assist from the load in the y direction. So this is then the sign is going to be plus. That is how you have to understand this. Now when you take the three-dimensional case, you will end up with one more term, mu into sigma z by E, and all the terms will be having a third term also. Okay, and for very simple way of understanding it, you learn this particular or by heart this particular figure, and for this figure you learn this equation, because this set of equation is defined for an element where sigma x, sigma y, sigma z all are acting or all are creating a tensile effect. There is no compressive load here. Suppose if you have a compressive load in any direction, you change the sign correspondingly. For example, if you have sigma z as negative, that means instead of sigma 3, if you have sigma z as negative or compressive load, then what will happen? We can say that if that is the case, then this is going to be plus, this is again going to be plus, okay, and this is going to be negative. That's all. It's a very simple thing. So if there is any change in the stress direction, kindly change the sign accordingly. That is how you have to define the Poisson ratio in 2 dimension and 3 dimension. This is a very simple way of learning it, but the actual way is by understanding the actual effect of the load. We will look whether the load is going to assist or it is going to restrict. If it is assisting, the sign has to be positive. If it is not assisting, opposing, it has to be negative. That is a simple and correct way of analyzing it. And if you find any kind of difficulty, this way also, that means by understanding the equation and the corresponding figure, you can also learn the other way also. Now, regarding the Poisson's ratio, the range, we have already told that the Poisson ratio of rubber is very much close to 0.5. And we have another material, it's a very common material, cork. Cork, Poisson ratio is close to 0. So, what do you understand if we say that cork has a Poisson's ratio of 0? See, cork is mainly used in wine bottles and like that. So what is the speciality of this material, or why it is used over there? It's very simple. See, if cork is having a Poisson's ratio 0, definitely the lateral strain is 0. That means even if you apply a load in the x direction, there will not be any kind of strain in the y direction. So this property will help to insert this cork into the neck of the bottle. Even if you apply a tensile load on the cork to cap it, there will not be any kind of lateral strains. If there is lateral strain, obviously you know the glass bottle is going to break, and that property will help to rigidly tight the cork into the glass bottles. Now, if we consider some polymer forms or origami folds, they exhibit negative Poisson's ratio. Negative Poisson's ratio means what? You apply a tensile load, but the material got contracted. Okay, or in other words, we can say that you applied a load and the effect was opposite in the opposite direction. Such kind of materials, they are also called as the NPR materials, negative Poisson ratio materials. Oxytic materials are some examples. And these materials, when stretched in y direction, they become thicker in the perpendicular direction. If you look at this particular figure, we can say that when a load is applied, what happened? It elongated in the perpendicular direction. You can see that the entire dimension was beyond this dotted line. That means it was supposed to reduce in the y direction, but instead of that, it got elongated. Such kind of behavior can be observed in the oxygen materials, and even if there are different structures developed also. Such a lot of data are available there on the internet. You can go and see. There are some interesting videos also. And if you go for some kind of carbon nanotubes, zigzag folded sheet metals, or honeycomb oxytic metamaterials, there are very few which exhibits a Poisson's ratio above 0.5 also in certain directions. So these are some of the commonly used Poisson's ratio. Anyway, for our subject, the ratio will be within 0.25 to 0.33. That is the way in which we are going to use the Poisson ratio. And more important is the relationship in 2-dimension and 3-dimension. Here you have to pay more attention in writing down the equations. We will solve some more questions using these relations. So that is how you have to learn and understand the Poisson relations. So kindly go through this relation and understand it. So thank you.